This talk is based on a recent paper with Jeff Pennington, Steve Schenker, and Zhendine Yang. And our paper came out at the same time as another paper by Ahmed Almiri, Tom Hartman, Juan Maldacena, Edgar Shagulian, and Amir Tajdini. Both of the papers had a large degree of overlap. So some references for this talk. I'm not going to give historical references, but recent references include the following. So the concept of quantum extremal surfaces in work by Faulkner, Lukowitz, Maldacena, Dong, Lukowitz, and Engelhardt and Wall. So that was a few years ago. Then about a year ago this month, so last May, there were a couple of really exciting papers, one by Pennington, one by Almiri, Engelhardt, Maroff, and Maxfield, applying this quantum extremal surface technology to compute the page curve of an evaporating black hole. And items 3 and 4, there are follow-up work to this interesting result too. And in particular, the paper that I'm going to be talking about on replica wormholes is a follow-up to the work in the papers marked 2. So let me just briefly review this page curve story. So this is a cartoon of an evaporating black hole. I drew the cartoon in flat space, but the story doesn't matter too much about that. So what's going on here? The red lines here are supposed to be the some Hawking radiation propagating out to infinity from the region near the horizon. And I've drawn both the particle that becomes the actual Hawking radiation far away, and I've also shown it's an interior partner of that particle. This is an approximate picture of Hawking radiation, where it consists of entangled quantum field theory fluctuations on the 2 sides of the horizon. One of them propagates out to infinity, and the other propagates into the singularity. But if we follow this process over time, then more and more of these pairs are produced, and it leads to an increasing amount of entanglement between the region outside of the black hole and the region inside, because the Hawking radiation outside is made up, it's 1/2 of these pairs, and the partners that it's entangled with are inside the black hole. So this builds up entanglement between the region outside the black hole and the region inside the black hole. Okay. So this problem was, I guess, first studied by Hawking, and his prediction, or the answer he would get for the entropy of the Hawking radiation, looks like this. So it grows. I drew an exactly linear function here. That's not too important. The important thing is it just keeps growing as time passes. It grows because more and more of these entangled pairs are produced, and the Hawking radiation outside is 1/2 of those entangled pairs, so it's entangled with the black hole. So in a little bit more detail, what Hawking's prediction for the entropy of the Hawking radiation would be is just the thermal entropy of the Hawking radiation. So Hawking radiation looks to a very good approximation like thermal, and Hawking's prediction for the entropy is just the thermal entropy of that amount of radiation. Okay, so that's a function that looks like this. Now, the problem with this function is that eventually, as time passes, that entropy gets bigger than the thermodynamic entropy of the black hole. And the black hole can't have more entanglement entropy, that is more fine-grained entropy, than its thermodynamic entropy. So what Page proposed was that the actual entropy of the Hawking radiation should be the minimum of Hawking's answer, the thermal entropy, that's the first term here, and the thermal entropy of the black hole, S, Bekenstein-Hawking. So Page's formula is the minimum of these 2 terms, and so I've plotted both of those terms here. The Hawking answer is just increasing over time, more and more of these entangled pairs. And the thermal entropy of the black hole is decreasing because the black hole is slowly getting smaller. They cross at some point. So Page's answer for the entropy of Hawking radiation would look something like this. It increases for a while following Hawking's curve, and then it just becomes the thermal entropy of the black hole, and eventually goes to zero because the black hole evaporates completely. Okay, so this is what the entropy of an evaporating black hole is supposed to look like, rather the entropy of the Hawking radiation of an evaporating black hole. And well, we've known for quite a while since Page's work that this is what the answer is supposed to look like, but we haven't known how to derive it from gravity. And in particular, if you'd asked a couple years ago, a lot of people, including me, would have said that it's a little bit unrealistic to try to answer this question, to how to derive this from gravity, because it sort of depends on the fact that black hole evaporation is a unitary process, and it seems to depend on a lot of sort of subtle details of the microscopic description of the black hole. It's a question about a fine-grained entropy, and in a sense, it seems like a very difficult question.
Douglas, general question. This entanglement entropy is the, if I want to make this statement precise, I want to know what entropy I'm computing exactly. So should I be trying to live on Scri plus and computing the entanglement entropy of the radiation up to a certain time with the radiation after that time?
Yeah. Well, you should just, yes, you could do that. As you'll see in a second, we're going to move to ADS, where it's a little bit easier to make this precise. But let's imagine that we have some slice along here, very close to Scri plus. We would compute the entropy of all the Hawking radiation that has hit Scri plus before this time. That's if we want to define it at infinity, and we probably should do that in the quantum gravity theory, but at least approximately we could define it on this blue slice here. We don't really need to go to Scri plus. We could compute the entropy of the Hawking radiation on this blue slice. And you could worry that the entropy in some finite region in a theory of quantum gravity isn't really well defined, and that subtlety appears, that's a subtlety that you could have worried about, but it appears to be unrelated to the actual resolution of this puzzle. So,
okay, and just one other quick question, which maybe you can postpone commenting on to later, but there's this, Suvrat, Raju and collaborators have had this paper recently saying that even on Scri plus, the idea of entanglement entropy of a certain region with the future is not very well defined, not 100% well defined concept. And if you feel like at some point, maybe you could comment on that.
Okay, well, yeah, we can talk about that. I doubt I'll have anything very helpful to say about it.
Okay, fine.
To be honest,
sorry.
I've sort of assumed that entanglement entropies can be defined at Scri plus, but I don't really know. In the ADS case, I know how to define them. At Scri plus, it's a technical question about whether you're allowed to insert twist operators at Scri plus, and I don't know for sure, but I assume that you are.
So can I just chime in here? You know, it's related to the old question, the earlier question that Shiraz asked. When you say Scri plus and you say entropy of Hawking radiation after Scri plus, that's itself not very well defined. I think you have to specify the subalgebra of Scri plus that you're looking at. So
okay.
There are many. I mean, you know, if you take the full subalgebra of Scri plus, then I think you wouldn't get this curve. So you need to specify. I mean, more precisely, what is the subalgebra for which you're looking at the entanglement entropy? You know, there's some operators at Scri plus, and you have to tell me what operators am I allowed to measure and what I'm not allowed to measure. If you measure all operators at Scri plus, then you know you would have all information near the pass boundary of Scri plus.
I think for the purposes of this talk, we don't even need to try to be as precise as going to Scri plus. We could just discuss the entropy of the quantum fields on this blue slice.
Very good, but then you have to, you see, but to get this page curve, presumably you have to measure like S-point correlators of quantum fields on the blue slice, right? You have to measure very high point correlators.
Well, you need to compute the entropy, yeah.
Correct, but I mean, to define it first, presumably you must be talking about a very fine-grained entropy on the blue slices as well.
Yeah, yes.
But then it wouldn't be valid to also be in some, quantum field approximation where you just take free fields and define the entropy like that. So I mean,
Well, I think it's valid for that region. It ends up not being valid for the rest of the geometry. So it's, like the interior ends up changing when you compute the entropy. But I think the region outside the black hole, nothing dramatic happens to it. You're right.
Okay, I'm really sorry for having started this disruption. Please go on, Dr.
yeah.
No. This is what I'm here for. So I'm happy to be interrupted.
Yeah, I mean, it's just a question of what the definition is. I think that there's, if we just say we'll take free fields and do the computation with that, then you don't expect to see the page curve really, right? So you're seeing like,
Yeah, it's important that there's dynamical gravity in the interior, but out here it's not important. So in fact, in a moment we'll move to a model where the radiation is living somewhere where there's no gravity at all, and that removes this subtlety. But even in this problem,
it would be well defined, yeah.
Even in this problem, we could put some kind of a cutoff here, and it's important that the gravity is dynamical inside the cutoff, and it changes the answer for reasons related to the type of thing you're discussing.
Yeah,
but
sure.
It's not important outside.
Yeah, maybe you should postpone it to later. I would agree with you that if you just switch off gravity at some point, then you have a well-defined quantity. The question is, maybe we can talk more about what happens if gravity is dynamical throughout. But please continue.
Okay. Yeah. So anyhow, many people, including me, would have been pessimistic about deriving this page curve from gravity. It's a little bit like, well, let me not say more about that. But the new answer to this is, well, we should at least try to compute it. It turns out that nobody had ever really tried to compute it properly before. So we should try to compute it in gravity using the replica trick and just see what happens. Okay. So I want to comment a little bit on somewhat a simplification of the question. So let's think about this black hole system partway through evaporation. And let's make some kind of a decomposition into a region outside the black hole, the Hawking radiation here, which we'll refer to as R. This will be made more precise below. And the black hole, which we'll call B. And the precise details of this decomposition aren't too important. But if we think about the state in this way, it looks like an entangled state between the state of the radiation and the black hole. So we could represent the state at time t as a sum over some number of states, where I with a subscript r is a state of the Hawking radiation, where I is some orthogonal basis, and psi I is a state of the black hole, where the interior partners of the Hawking radiation are in state I. So we get some huge sum of terms where we have Hawking radiation in some state I, and we have a black hole where the interior partners are in the corresponding state. And the state of the black hole with that state of the interior partners is called psi I. So B stands for black hole, R stands for radiation. Okay, and the basic point that underlies the page curve, the basic thing that we need to explain is the following. Even if you put lots of stuff behind the horizon, lots and lots of interior partners, whatever you want to put back there, somehow you can't get more than SBH, that's Bekenstein-Hawking amount of entanglement with any other system. So at very late time in an evaporating black hole, it looks like you're going to get a huge amount of entanglement between R and B because you have a very large number of these Hawking partners. But the claim is that you can't get that much entanglement because no matter what you put back here, the entanglement of the black hole with the radiation or with any system can be no greater than S Bekenstein-Hawking. So that's sort of a sharpening of this page curve phenomenon. And the goal in the rest of the talk, well, most of the rest of the talk, will be to show how this happens, how this limit arises, in the simplest possible model that we can find. Okay, so let's now move away from the evaporating black hole to this model. We're going to try to isolate and analyze this question in a simple toy model.
Douglas, can I just ask a question, please?
Yeah.
So you are implicitly assuming that there are black hole microstates in this wave function psi I?
Yes, yes. But they're not these states psi I are not necessarily orthogonal or anything. They're just some description of whatever the state of the black hole is when it's emitted Hawking radiation in state I.
Okay, all right, thank you.
Okay. Okay, so let's now move to starting to describe the problem that we're going to study in more detail. So we're going to put away the Penrose diagram of the evaporating black hole and examine this somewhat simpler Penrose diagram. So what do we have here? This system here is a black hole in asymptotically anti-de Sitter space. So here's the anti-de Sitter space boundary. Here's the horizon. And what we're going to do is we're going to just put some stuff behind the horizon of the black hole. The stuff is represented by this blue curve here. And it's going to be, in the back of our mind, we know that it's supposed to represent the interior partners of the Hawking radiation. But that's not too important. The important thing is just that it's some stuff that we've put behind the horizon of the black hole, and it can be in one of k different internal states. So you can imagine some kind of particle with an extremely large number of internal states, or some brain that we put back here. It can have k different internal states, just like the interior partners of the Hawking radiation can have a very large number of different internal states. Okay, and what we're going to do is we're going to take that system and entangle it with a reference system R, which is mocking up the radiation. And we're going to consider this state here, a superposition of k different terms, where the reference system is in state I, and then the black hole system is in a state psi I, where what psi I means is we have a state of the black hole where the thing behind the horizon is in state I. So thing behind the horizon, state I, and radiation in state I. And we've taken entangled sum. Okay, so the whole game will be to try to compute the entropy of the radiation system R. And Hawking's answer for the entropy of the radiation system would have been just the naive answer you get from looking at this setup, which would be logarithm of k, the log of the number of states. So here we have a maximally entangled state with k different terms. So the naive answer for the entropy would be log of k. And on the other hand, Page's answer would be the minimum of Hawking's answer and this absolute maximum, the entropy of the black hole. So Page says the entropy is similar to Hawking's formula, but with an added rule that the entanglement between the black hole system and R can never be bigger than the entropy of the black hole itself. Okay, so this is just this is analogous, an analogy to the Page curve discussion.
Douglas,
Yeah.
I have a question here. This is Dr. So in terms of this, pure states work of Kuklu and Maldacena, can I think of the psi I B states as the spin eigenstates of the SYK model? Like
yeah, absolutely. That's a great model, and actually, yes, that's a good model for this.
Okay.
Yeah, so then you would think of SYK as representing the black hole, and you would take an entangled superposition of those Kuklu-Maldacena states with some kind of reference. And yeah, that's an excellent example to think about. Okay, so all right, so let's now try to analyze this problem in a little more detail. So we're going to do this again in our search for the simplest possible version of this problem. We're going to work in 2 dimensions and consider JT gravity, Joukiffe-Teitelbaum gravity, and we're going to represent this blue thing behind the horizon as an end-of-the-world brain, the type of thing that was studied in the paper that Gautam just reminded us of. So the action for our two-dimensional gravity theory is the following. We have the action of JT gravity. So that's written here. I'll discuss it in a second. And then we add to it a action, which is just the tension of these end-to-the-world branes. So we couple JT gravity. Yeah.
Can I ask a question, Douglas? So I was a little bit confused about, can you go to the previous slide, please?
Mm-hmm.
Yes. If we are to understand these microstates as the Kulkulu-Maldacena states, I would imagine that those states are actually living on the right boundary. I mean, you know, so this is something which you have introduced, to get a certain type of geometry, but I don't understand why this system on the left-hand side has k internal states. I mean, that's some model that you put in by hand, or because the Kulkulu-Maldacena
it's shared. It's something. Well, in this model we just put it in by hand, but the setup that you just described is an example of it. So in that case, the this whole system here would be like the SYK system, and the state of that system, psi I, would be like a Kulkulu-Maldacena state with a particular spin microstate.
Okay. But sorry, I had the same question as Spenta, which is that I would have thought that the state of the full system, as you're saying, up till the right boundary, Douglas, would be then the Kulkulu-Maldacena state, and that would entangle with IR. So in that way, I would agree with your final description, that entangled formula, but I wouldn't ascribe the state to the degree of freedom you've introduced behind the horizon.
At the brane. Oh, well, this isn't some other, this boundary here is not associated to another quantum system. This isn't like another ADS asymptotic boundary. This is just an end-of-the-world brane. So this degree of freedom is encoded in the asymptotic boundary here, holographically.
Right. I guess, at least I think this is what Spenta was saying, and I was thinking is that the full state, you know, of the entire ADS2 region, including your end of the world brane, is what we would call psi IB. And that would include all the degrees of freedom in the end of the world brane. But it wouldn't necessarily be in one-to-one correspondence with the end of the world brane states, or it wouldn't just be the end of the world brane.
Oh, it's labeled by the state of the end of the world brane. Maybe what's bothering you is that in the Kulkulu-Maldacena setup, the bulk is a little bit different everywhere. Like it knows about the state I even over here.
Yeah. And
in the model here, I've assumed that that dependence is localized at the location of the brane. Is that the thing that's bothering you?
Yeah, in part, yeah.
Yeah, well, that's a slight difference between this slight detailed difference between this setup and the Kulkulu-Maldacena setup. But the important thing is really just that it's, well, the thing we're trying to mock up is the interior partners of the Hawking radiation. And then the distinction between the states is indeed behind the horizon of the black hole. So this is a good model of that.
So, I mean, sorry, you should go on, but basically the end of the world brane actually, in a sense, is going to represent the island degrees of freedom, just to jump ahead, right? It's the partners of the Hawking.
The island will be everything inside this black dot here. So it will be,
All right, okay.
So, Douglas, the outgoing quanta, why are they not also dual to the boundary degrees of freedom?
So the analogy here is that the outgoing quanta have left the system. They've been sucked out of the. So suppose this was n equals 4 super Yang mills. What we did was we coupled n equals 4 super Yang mills to some other system and extracted some energy out of it. That energy is now in system R. That's the Hawking radiation. So it's no longer in the system at all. But the interior partners are still...
If you consider evaporating black hole dual to a conformal field theory, then the entire description of this process would be given in terms of the conformal field theory.
Well, but a better analogy would be to describe an evaporating black hole as a conformal field theory coupled to some kind of a bath where the conformal field theory can leak energy into.
Okay.
It's like we're describing the evaporation of a big black hole in ADS. where in order to get it to evaporate, you need to allow the quanta to leave the ADS space altogether.
Okay, thank you.
Yeah, that's the cleanest setting to discuss this problem, but actually it doesn't matter. We could do it in the type of setup that you were describing as well. It's just a little harder to phrase it in terms of the CFT. But the essential bulk physics is behind the horizon, so it doesn't matter about these details. Okay. Okay, so let me go on. So we were describing this end of the world brane plus JT gravity action. So we have this tension term integrated along the world line of the end of the world branes, and then we just have the standard JT gravity action. The JT gravity action consists of these two terms. Don't worry too much about this term. I'll sort of take care of that term behind the scenes to the extent that it's relevant. The term that I want you to focus on is the first term, where S naught is a parameter. You should think of it as a large parameter proportional to the entropy of the black hole. And chi is the Euler characteristic. So, and actually we're going to be doing really easy topology where the only value of the Euler characteristic we'll need to know is its value for the disk. So for a configuration with the topology of n separate disks, chi has the value n. So don't worry too much about this term. And for the action of JT gravity, just think of it as minus S naught times the number of disks. Okay. Classical solutions in this coupled theory, examples of those are shown below here. Euclidean signature on the left and Lorentzian signature on the right. So this blue curve here is the end of the world brane, and the black curve is the asymptotic ADS boundary. So you can think about this as, well, JT gravity has hyperbolic space as a solution. So you can think about what I've drawn here as a portion of the hyperbolic disk. This black curve is like a constant radius locus in the hyperbolic disk. So it's like part of a circle in hyperbolic space out near the asymptotic boundary. And the blue curve is part of a geodesic, because the action for the end of the world brane wants that thing to follow a geodesic. So this is a classical solution. We have an end of the world brane following this geodesic, and then we have the actual boundary of the JT gravity region as a circle in hyperbolic space, a big circle. Okay, now here's the same solution in Lorentzian signature. And this end of the world brane is behind the horizon of a black hole. Here's the asymptotic boundary of the black hole. Here are the horizons. And a point that's going to be important for us is that the two geometries share the same t=0 surface. So this surface is the same. It's present in both the Lorentzian and the Euclidean geometries. And that's where we'll think about our state as living. So let's think about the state we want to describe. We're going to let this end of the world brane have k possible internal states. And we're going to study a state of a combination of the JT gravity system and a reference system. So psi I subscript b means a state like this one here, where the end of the world brane is in state I. And the other term I subscript r is the state of the reference system that we've entangled it with. Okay, so for the next few slides, we're going to be drawing Euclidean pictures. We're going to be thinking about this diagram on the left, and not so much the diagram on the right, but the state that we're interested in at t=0 can be accessed through either of them. Okay.
Douglas, a question here. Hello.
Hi.
Yeah, hi. So I just wanted to ask, so this end of the world brane, is it like the dimension of the entire Hilbert space of this entire end of the world brane is given by k, or is it like only some relevant subset of the end of the world brane which is entangled with the radiation? That
it actually doesn't matter. Either of those will work fine for this discussion.
So
the important thing is
k is then a fixed number, or or not?
So, sorry, could you say it again?
K is then a fixed number, like.
Well, we're going to be studying things as a function of K. We're going to study it as a function of K, and we're going to consider the case where K is very, very big.
I see. Thank you.
So in order to generate a puzzle here, right? In order to get too much entanglement between the black hole and something else, we should take K extremely big. And that's what we're going to do. And then we're going to see what happens.
And sorry, Douglas, just to ask you about that. So you could in particular have then in your model a end of the world brane hidden by a black hole of some entropy, where the total number of degrees of freedom of the end of the world brane far exceed the entropy of the black hole, if I understand.
Yeah. That's exactly the regime that we want to be working in, because that sounds like something weird is going to have to happen there.
And that would be allowed in your model.
Yes, that would be allowed, but we'll see that gravity is smart enough to deal with that case appropriately.
Okay.
Yeah.
Thanks.
I mean, the case that you're describing is exactly what a black hole at late times looks like. At late times, it's one where you just have way too much stuff behind the horizon, and way more than the entropy of the black hole. And the surprising fact is that gravity is smart enough to deal with that gracefully. And we're going to see how that works in this simple model. Okay, so this is the state we want to study. Okay, so now let's get to work. As you'll see, the bulk geometry here, the two-dimensional geometry, is kind of a slippery concept. It kind of moves around depending on exactly what question we're asking, and it's best to sort of ground our thinking in the boundary conditions. So let's get some practice with the boundary conditions we're going to be discussing. So first, let's think back to this Euclidean solution, where we have the end of the world brane following this geodesic and the boundary following some circle. This Euclidean solution is a solution to the following boundary problem. We put the following boundary conditions. We have a segment of the asymptotic boundary with some fixed length and with a fixed value of the dilaton. So that's the black line. And then the additional boundary data is at the ends of the black line where these two blue circles live. We say that an end of the world brane needs to meet the boundary at those points. So an end of the world brane needs to intersect the boundary at this point, and an end of the world brane needs to intersect the boundary at this point. And in between, there should be some asymptotic boundary of fixed renormalized length and fixed value of the dilaton. So if we try to find a solution to the equations of JT gravity with those boundary conditions, we'll find this thing here. It has a boundary of some length, which we can adjust, and an end of the world brane intersects the black line at this point and at that point. Okay, so the actual value for the path integral, the JT gravity path integral on this space here, gets interpreted as the normalization factor, psi I hat, inner product psi I hat, for an unnormalized state of the black hole with an end of the world brane behind the horizon.
Douglas, sorry to interrupt. Suppose you had a UV description of the system, something like an SYK model. Then on the black line, all you really have is the field theory degrees of freedom.
Yes.
So these blue dots at the end would be the specification of a state, would
yes.
be specification of the state in the Hilbert space of,
yes.
of the UV description.
Yes.
So from the UV point of view, you're just specifying a state in the Hilbert space, and the bulk takes that and interprets that as if states on this effective end of the world brane. Is this right?
Yes. Yes. Yeah.
Thank you.
This is also true in higher dimensions, that like a boundary in the CFT is represented in the bulk by an end of the world brane that meets the actual ADS boundary at that locus. And the type of end of the world brane depends on the boundary condition that you put in the CFT.
Thank you.
Okay, so so this quantity here, the path integral here, should be interpreted as a normalization factor. It's a inner product of a state with itself. where the state is the one, to use in Shiraz's language, we start with some state in a boundary, with some boundary state here, and then we evolve for some Euclidean time, like beta over 2 or whatever, to get to this point. And this full contour here is computing the inner product of 2 copies of that state. We put the state here and evolve it beta over 2 to this point. And we put the same state here and evolve it beta over 2 to this point. So the whole thing is computing the inner product of some state with itself, where that state is defined by starting with a particular state and evolving for Euclidean time beta over 2. Anyhow, the actual answer for the path integral is something that can be computed exactly, but the only part that we're going to need for the discussion is this Euler characteristic part. So we can approximate this inner product as e to the s0 times the Euler characteristic of this manifold. It's topologically a disk, so chi is 1. So this is, roughly speaking, e to the s0. Okay, so that's the first computation out of the way. As the next step up in complexity, let's consider the boundary conditions.
Sorry, Douglas, to interrupt you. Just to understand
no
the bulk, just to understand the bulk computation, the end of the world brane had a mass mu, as you said, and therefore interacts with the gravity theory. But what about the degrees I at the end of the world brane? Do they interact in any way besides the mass? With the
I is, it's like the I is like a species of the end of the world brane. So let's assume that we have k different possible end of the world branes with mass mu.
So besides the mass, nothing else interacts with the gravity degrees of freedom.
Yeah, for the simplest case is that one, right? Right.
Okay. Thanks.
All right. The gravity theory doesn't care about the value of I except at the endpoints where it intersects asymptotic boundary. So, well, continuing actually along those lines, let's try to compute the next simplest thing, which are the boundary conditions for an inner product of 2 different states. So between states of the black hole, in which the end of the world brane is in 2 different states, I and J. So the boundary conditions look like this. It's similar to what we had before, but this blue dot here has an index I associated to it. So the boundary condition at this point says that an end of the world brane of type I needs to hit the boundary here. And the other boundary conditions at the other end says that an end of the world brane of type J needs to hit the boundary here. So a geometry that fills in these boundary conditions is the following one here. It's just the same thing we were looking at a second ago. And it's proportional to e to the s0 times Kronecker delta ij, where we've assumed that, yeah.
I have a question, Douglas. So a short while ago when you began, you said that the states psi I were not necessarily orthogonal, and that sort of fitted in with the SYK states, these overcomplete set of states, low energy states. But those are overcomplete and therefore not orthogonal. So
yes,
what is your picture of these?
You will see. You will see. You will see. These aren't orthogonal either, despite first appearances.
Okay. Okay.
Stay tuned. This question you're asking is really the heart of the matter. So I don't want to try to answer it now because the next couple slides will be answering it.
Okay. Thank you.
But so far, okay, forget what I just said, and we'll come back to it. But for now, let's just say that the geometry that computes this inner product is this one, and it's proportional to delta ij. So we find that these states are orthogonal. Now, we can use this information here to do the computation that we wanted to do. Remember what we wanted to do was in this state here to compute the entropy of the system R. And we can do that by computing the density matrix for the R system in that state. That's equal to this expression here, where the psi hats are unnormalized versions of the states, and we normalize them by dividing by e to the s0 here.
Sorry,
and now we just plug in. Yep.
Douglas.
Yes.
Sorry, it may overlap slightly with the previous comment that you made, but here you say in the first line, between the states of black hole with end of the world brains in orthogonal states. Here you are assuming orthogonal states, but in this computation you say we get delta ij by this geometry. So are they assumed to be orthogonal, or you are computing this inner product and finding it to be delta ij, proportional delta ij, or
yeah, good. Let me try to
also you are
clarify.
using psi hats here while there you had psis.
Okay, good. Let me clarify both of those things. So the first question is an important one. What am I? Okay. What are the states psi I? These are states of the black hole where we put an end of the world brain in state I. And we're free to choose a basis for the states of the end of the world brain. And we can pick a basis where they're orthogonal. And that's what we've done. That means that the propagator for the end of the world brain is proportional to delta ij. Now, this computation isn't completely trivial because what we're computing here is not directly an inner product of the states of the end of the world brain. It's an inner product of two states of the black hole. And it turns out that in order for that inner product to be non-zero, the end of the world brain has to be able to sort of propagate from one side to the other. So in fact, the orthogonality of the two states of the end of the world brain implies the orthogonality of these two states of the black hole. But in principle, they were slightly different computations. So it's almost completely trivial, but not completely trivial, that this inner product is proportional to delta ij. So the second question you asked was about the psi hats, and psi hat just means an unnormalized version of the state psi. So psi hat is a normalization which is natural from the perspective of the gravity computation. And to convert to the density to the state here where we have psi's, these are normalized versions. I've put this factor of e to the s naught here. So we could absorb the e to the s naught into this factor here and turn these psi hats into normalized states psi. But it's going to be easier to work with the unnormalized states because the boundary conditions for those things are, well, they're just more natural in gravity. Okay. Okay. So our goal was to compute the density matrix, well, the entropy of the R system. And we've succeeded in computing the density matrix now. And what is the answer that we got? Well, we found that this density matrix here, it's 1 over k times this sum over k different orthogonal projectors. So it's a maximally entangled it's a maximally mixed density matrix. It's proportional to the identity matrix. So the radiation is in a density matrix that's maximally mixed. And the entropy of a maximally mixed density matrix on k states is log of k. So that's the Hawking answer that we were expecting, this answer here, just the naive entropy of this maximally entangled state. A useful thing to compute that we'll discuss in a second is the purity. It's a little bit simpler than the entropy, but it's also sort of a measure of the entropy, trace rho squared. And if you compute trace rho squared for this density matrix, you find the answer 1 over k. There are k terms, each of size 1 over k squared, so the sum is 1 over k. So it's in thinking about the purity and the entropy, it's helpful to keep in mind that big entropy corresponds to small purity. So by making k very, very large, we can make the entropy of this density matrix huge. Log k gets very big. And we can make the purity extremely small. 1 over k gets very small. And it looks like from this computation that we're going to be able to make the entropy as large as we want. So by making k as big as we want, we can make the entropy as big as we want. And that's a problem because the entropy is not supposed to exceed the thermodynamic entropy of the black hole. So what we're looking for is an answer like this, the minimum of log k and S black hole. But what we found was just log k. So far we haven't succeeded.
Sorry, Douglas, just to see if I understand your previous comments about orthogonality. So is the point that the state that you constructed in the beginning, psi I and I entangled, there psi I, which is the state of the end of the world brane, can be taken to be in orthogonal. It can be taken to be orthogonal. But while here, this inner product is not quite that inner product in the end of the word brane system, but rather as a black hole system. And that's why you need a computation for it to show that the inner product is proportional to delta Ig.
I agree with the second part. I'm not sure I understood the first part. In this state here, let me try to clarify in this state. So in this state here, the states I in the system R are exactly honest orthogonal states. That's just some basis that we've picked of the radiation system. These states I are honest to God orthogonal states.
Okay.
The states psi I, a priori, we don't know if they're orthogonal or if they're not orthogonal. Our definition of them is they're a state of the black hole where we have an end of the world brane of type I. And then we do a short computation. We label our end of the world branes by an orthogonal basis of end of the world brane states. And we find that that means that these states are also orthogonal. So,
okay.
Sorry, Douglas, can I just ask, maybe follow up? But anyway, I mean, you've sort of set up a system where to begin with, you allowed, at least as far as the end of the world brane is concerned, in principle, many more states than the black hole entropy.
yes.
And what's then what the system is going to do, I'm sorry if I'm jumping ahead, please excuse me, is, as you said, there's a conceptual difference between the state I and the state psi I, because the state psi I represents the state of the full gravity theory.
Yes.
And the only consistent way is that the number of independent psi I states, in a
Yes.
sense, can't exceed the black hole entropy. So
Yes.
the psi I, psi j orthogonality has to be violated for that to come about.
Absolutely.
But if I may say, so I'm sorry, you should of course go on, but if I may say, I mean, it may be a consequence of your model where you put in the end of the world brane degrees of freedom, many more states than were allowed for the black
Yes.
hole in the first place. That's what seems
Well,
a little artificial to me.
Well, but it happens here. It happens here. There are many more states of the interior partners than the entropy of the black hole. So we're just trying to model that. Anyhow,
Okay.
Okay. We can now get, this problem has a solution. So I phrased this first calculation. This is similar to Hawking's calculation. And we found a problem. We found that the entropy can get too big, as you say, it can get bigger than the entropy of the black hole. So now we need to see how the problem is resolved. So to resolve the problem, let's start by computing the purity. So what we're going to do is compute the purity directly. So instead of first computing rho and then computing the entropy of rho, let's just compute trace of rho squared. Ask what gravity says the answer is to trace of rho squared. So I can use the formula for rho and find this expression for trace of rho squared. It's a sum of squares of these inner products. Okay. Now let's write down the boundary conditions for the square of this inner product. So just one of those copies of the inner product would be boundary conditioned like this. We have a segment of the boundary with end of the world brane boundary conditions I at one side and J at the other. And the complex conjugate is the same thing, but with this arrow in the opposite direction. So we have two copies of this same boundary condition. And the essential point, the point that underlies all of this stuff, is that there are two different ways of filling in these boundary conditions. There's one way where we fill them in sort of separately and independently. We get two copies of the same calculation that we did on the previous slide, two copies of this disk. But another thing we can do is we can fill it in with a connected geometry, like this one here. This is also a valid solution with these boundary conditions. Okay, so if you ask gravity what the answer for the quantity on the left-hand side is, it tells you it's the sum of these two terms. So let's take that answer and stick it into the formula up here for the trace of rho squared. And let's just do some simple counting. So let's first look at the first term. So when we contract I and j with j, we're going to have one loop of this dotted index. That one loop is going to give us a factor of k, the number of states of the end-of-the-world brane. So that's this factor of k. We have two disks, so the order characteristic is 2, and we get the factor e to the 2 s naught. So that explains the first term. Let's now look at the second term. When we connect j with j, we get one index loop here, and we get another index loop there. So we get k squared, but there's only one topological disk, so we get k squared times e to the s naught. So that's the answer that gravity gives for this sum here. When we divide it by the normalization factor out front, we find trace rho squared is equal to 1 over k plus 1 over e to the s naught. The first term comes from this, the second term comes from the connected geometry. And if k is extremely large, then the connected geometry, this is a replica wormhole, is going to dominate. So it's called a replica wormhole because these two copies of the boundary condition are associated to the two replicas, the two copies of rho, the two of these factors. And it's a wormhole because the two asymptotic boundaries are connected by a geometry. So this replica wormhole is insignificant if k is small, but if k is really, really big, like bigger than e to the s naught, then it dominates. Okay. So this is going to solve the problem with the entropy. We're going to use this to compute the entropy in a moment, and we're going to see that this gives us the right answer for the entropy. It corrects the Hawking answer and gives us the Page answer. But there's something that you guys are probably feeling uncomfortable about, and I think it's part of what was motivating the questions before, and I want to get right into it because I'm also uncomfortable, but I think it's really interesting. So let's discuss this. Basically, I imagine what you're thinking to yourselves is that this answer for trace rho squared seems to be in tension with what we had computed before, right? We computed rho, and sorry for jumping around, but we computed rho and we got this answer. We found it's maximally entangled, maximally mixed, and its entropy is, sorry, its purity is 1 over k. So we computed rho, we computed the purity, and then we computed the purity directly and we found a different answer. So why did we find these two different answers for exactly the same thing? So the disagreement between the two answers, just at a technical level, we'll try to interpret it in a moment, but just at a technical level, the disagreement is due to the following contradictory statements that gravity gave us. One statement was this one, the orthogonality of these states. And the second statement was this one. When we had two copies of this boundary condition, then there are two ways that they can be connected together. And those two terms lead to these two terms here. This is the disconnected configuration, and this is the replica wormhole. So these two answers are literally inconsistent. The right-hand side over here is not the square of the left-hand side. So now we have to try to interpret it. This is what gravity told us is the answer to our question. We're supposed to try to interpret the answer. And here's one attempt at an interpretation. Let's imagine that the inner product between these two states is equal to delta ij plus a very small and random term, plus a small kind of erratic correction. So this is a big piece, and then we have a small correction. Then the formulas that we computed before could be interpreted as ensemble averages of this expression here. So the expression that's highlighted blue, if we average that over some ensemble for the erratic term r, where r has 0 mean and it has a variance that's equal to 1, then we'll get exactly this expression here. So we'll find that these two equations are not consistent with any particular answer for the inner product, but they are consistent with an ensemble of answers for the inner product. So an attempt to interpret these contradictory answers gravity is giving us is that gravity, at least in this model, wants to be describing not a specific quantum system, but an ensemble average over them. And that ensemble average is somehow implicit in the gravity description. Okay.
Are you saying gravity has inherently some disorder or something? I mean, in the context of SYK model, of course, there is a disorder.
Yeah.
But now we're talking about JT gravity. So where is the disorder coming from?
No, there's a brain. End of the world brain is there, right?
But yeah, that's in a particular model. But let us say that, you know, I don't care about a particular model. I mean, I have some quantum theory, which includes the quantum theory of the end of the world brain. And where is the disorder? I mean, what's the picture of the disorder in general?
Well, let me make a comment which might be helpful. I don't know. Let's discuss for a second pure JT gravity. Pure JT gravity without end of the world brains, just ordinary pure JT gravity, is not holographically dual to a quantum system. It's holographically dual to an ensemble average of quantum systems. It's dual to a matrix integral. So there's no explicit disorder in the gravity description. What you have in the gravity description is wormholes. And those wormholes are dual to an ensemble of boundary theories. So it's similar to the discussion of Coleman from the 80s, and Giddings and Strominger, Polchinski, a bunch of people have discussed these ideas that wormholes in a gravity description, Euclidean wormholes in gravity, can be interpreted as an ensemble of theories. And in JT gravity, it's definitely true. And in this model with brains that we've been discussing, JT gravity with brains, it's also definitely true.
Can I ask a question actually here?
Yeah.
So, I mean, we also know that JT gravity has a Hamiltonian description. You know, you can do the ADM type of Hamiltonian description of JT gravity. Or is it this multiple boundaries that you're introducing that invalidates a Hamiltonian description of this type of problem?
Well, I think, so JT gravity has a Hamiltonian description on some fixed topology. So like if we study JT gravity on the disk topology, then we can quantize that.
Yes, yes.
But a quantum theory of gravity shouldn't have a topological restriction. You should sum over all topologies. And when we sum over all topologies, we find that it is dual to some kind of quantum system, but it's not a specific quantum system. It's a matrix integral.
But the Hamiltonian usually doesn't change if you have underlying topologies, like take 1/n expansion in a gauge theory. You know, you're summing over lots of topologies of the you know, planar diagrams, but the underlying Hamiltonian doesn't change. It's the same. I'm a little confused about this problem.
In this case, in the analog to a large N gauge theory, the Hamiltonian that I'm discussing would be like one of the gauge fields, or one of the n by n matrices. So the integral in the path integral of the gauge theory would be on the ensemble of the Hamiltonians.
I see. Okay, thanks.
So, well.
Sorry, Douglas, you should complete, but I have two questions at whatever stage you feel.
No, go ahead, go ahead.
Okay, if I can just go back to this point about gravity computing average answers. You can have a situation where one would expect in a fairly manifestly unitary theory that you get the JT model as a good approximation, which is if you take a near extremal black hole in 4D, say in a supersymmetric theory, where the number of states at the ground states can be counted with, you know, exquisite precision, and agrees with the Bekenstein-Hawking entropy, the near extremal behavior does get reproduced very well by JT gravity, as you know. And in a situation like this, if you were to repeat your arguments, where would the averaging then come from? Now, Ashok, I don't know if Ashok is here, but Ashok made a very interesting suggestion. He said there's a huge ground state entropy for these situations. And maybe it comes because you average over those number of ground states. I don't know, that remains to be seen. But I just wanted your views on that. And the reason I partly ask is, even if that were the case, and you were trying to model it by associating those degrees of freedom with the end of the world brane, you wouldn't put in more degrees of freedom than the ground state entropy. Whereas here you're doing that, so at least to begin with. So, and then discussing consequences. So all right, this was my question. More specifically, just if the claim is that in general, JT gravity, no matter where it arises, always corresponds to some kind of a average system, not a unitary theory, then how would it work in situations where we know there is an underlying unitary theory?
Okay, good. I understand. Yeah, I understand the question. So we could imagine that JT gravity is an effective low energy description of a more complete theory. So the case you described of some kind of near extremal black hole in some interesting higher dimensional theory of quantum gravity, that theory is not exactly JT gravity. It's JT gravity plus stuff. Mm-hmm. And I'm not making any claim that JT gravity plus stuff is always dual to an ensemble. And in fact, we have excellent evidence that there are many theories of quantum gravity that are not dual to ensembles, maybe almost all of them. And the difference has to be somehow that the extra stuff you have in those theories, strings, branes, propagating matter fields, that stuff is important for making the theory not an ensemble average. The statement I made about pure JT gravity is really just restricted. Well, we have just one data point, right? Pure JT gravity is definitely dual to an ensemble. And well, n equals 4 super mils is definitely not dual to an ensemble. So it looks like quantum gravity can do both types of things. It can be dual to ensembles, and it can also be dual to specific quantum systems. Okay. The point that I want to highlight here is that in this computation, it seems like the replica wormholes can give you an answer for the entropy, but sort of at the cost of, well, at least, well, I don't know. I don't want to claim that it's the only possible interpretation, but at least in this model, they have to be interpreted in terms of an ensemble. In other cases, with more matter fields and some interesting theory with interesting UV completion, I don't know, and I don't want to make a claim that it's an ensemble average, but I am confused about that case.
Can I make a comment?
Yeah.
You see, one of the things you're doing is that you're looking at JT gravity with you know, lots of boundary conditions, lots of boundaries basically. Now, if you think about higher dimensions also, if you want to compute something like purification or something, then would you not have wormholes connecting those boundaries of the higher dimension stuff that you will do? I mean, I'm just extrapolating from this calculation of yours. The disk is replaced by some ADS space and, you know, with lots of boundaries. And there would be configurations connecting those boundaries the way you have been saying here.
Yes.
And yeah, so, yeah, okay. I just wanted to say that maybe those theories then also could be understood as ensembles by the same type of logic, actually, because there also maybe, you may find equations like the one you have. Those contradictory equations are there, which you could reconcile by considering an ensemble.
Yeah, exactly. So there's an analog of these contradictory equations, like in this paper by Maldacena and Maus, that anytime you have Euclidean wormholes in ADS-CFT, there's a similar kind of contradiction.
I see.
So the fact that these replica wormholes, well, one point I want to make is that there's no direct contradiction for the entropy. The direct contradiction is in these inner products. So the computation of the entropy by itself doesn't immediately lead to any problem. It's when you try to interpret the computation of the entropy in terms of data about these inner products that you run into trouble. So it could be that we're not allowed to do that step in this theory, but well, sorry, that we're not allowed to do that step in more interesting higher dimensional examples. But in this theory, we can do that step, and we find that it has to be an ensemble.
Sorry, actually, Douglas, sorry, just one sec, Shiraz, then you should, of course. Sorry, actually, there was something basic I wanted to ask in your model, which was if you just computed the partition function at temperature T, so your one continuous boundary of length beta, and the end of the world brain does whatever it does consistent with that. What is the answer you get?
Oh,
how does
I'm
it
not
scale
sure.
with K?
No, I don't know what you mean by the partition function when we have the end of the world brain. You can compute I think the closest thing to that would be this unnormalized inner product, this thing. I mean, normally for partition function, you want to have a circle for the boundary.
Right, right.
If you have these end of the world brains, you have some kind of interval. So it's like an inner product of states. It's not a trace.
But then shouldn't you take two intervals of length beta over 2 and join the two to get the, and sum over the indices? Would that not be the partition function?
And sum over the indices that end of the world brains?
Yeah. I don't know, I'm asking you.
Well, that's actually exactly what we computed here. So that's this computation. That's the Renyi entropy. It's not quite a partition function.
I see. But shouldn't there be a well-defined answer? What is the partition function of the system at temperature T?
Well, yeah, but the end of the world brain is like an initial state in the boundary theory, or a final state. So the end of the world brain represents a state in the boundary theory. And so you have to ask, in a partition function at temperature T makes no reference to a state. So if you want to combine the concept of a partition function with the concept of a state, then I guess you have to tell me exactly how you're doing that.
Okay. All right. Thanks.
Hello.
Douglas, just to make sure I'm completely understanding the discussion over the last 3-4 minutes, you seem to be saying that naively, the mechanism that you're proposing for information, for the resolution of the information loss puzzle in this talk will naively not apply to n = 4 Yang-Mills theory, assuming that is one theory, not an ensemble. Is that correct?
Well, let me try to answer it as accurately as I can, because it's an important question. The most conservative statement is that in order to apply this to n = 4 super Yang-Mills, we wouldn't be able to get a satisfactory interpretation in terms of these inner products. So we would, let's say in the bulk dual of n = 4 super Yang-Mills, we could compute the entropy and probably get the right answer from some replica wormholes. We would then try to interpret those replica wormhole calculations. And to try to interpret them in terms of quantum mechanics like this, I think we would fail. In other words, we would have to view those replica wormhole calculations as giving us some kind of coarse-grained approximation. And then in the literal computation of the entropy, some kind of UV physics would have to be relevant that would restore this well.
Yeah, thank you.
Well, it was a poorly phrased answer, and it's largely because I'm confused about this, so I don't know. I don't have a great answer to give. I probably could have given a better answer than I did, but I definitely can't give you a great answer.
Sorry. So, Douglas, I had a question, which is kind of follow-up of these questions. So let's say we take one of these, like extremal black holes where we know that the black hole counting, we can count the microstates and get the entropy.
Yeah.
Then, we can calculate something like purity. I guess nobody has done it, but let's say if you could somehow calculate it,
presumably there'll be some wormhole contributions on the gravity side. So if the statement that, like if you calculate it on the other side, and if you calculate it, if you calculate purity on the gravity side, they won't match, because in somehow gravity is, the wormhole contributions on the gravity have this average description.
I think there must be additional things in that calculation. So you would compute the wormhole from gravity, and then you have a bunch of other stuff too that I don't know exactly what it is. And okay, I can try to answer both this question and Shiraz's question a little better. Let's imagine that we're doing this calculation in the bulk dual to n equals 4 Supering mills.
Okay.
And we ask this question in gravity, and we find some contribution from a wormhole. So, sorry, I'm going to describe a fantasy for how it works in n equals 4 Supering mills, or the kind of theory that you were just asking about, Sufra. So, a fantasy is that you will have the wormhole contribution, and you'll have a whole bunch of other stuff. And that other stuff will give a big correction to these quantities, to these answers, to the answers for these inner products. And it will give such a big correction that it restores the mathematical validity of the equations. But it will give some kind of a big correction that sort of averages out when you sum over I and j. So that if you just care about the sum of these things over I and j, then you can use the gravity wormhole. So that if you only care about this sum, then the wormhole description is good and it computes the entropy for you and you're happy. And then when you try to ask about the actual terms that go into the sum, like the guts of the calculation, then all this other stuff that we don't know what it is has to be relevant. Some kind of contributions from brains or fuzzballs or something has to compete with the wormholes and restore mathematical consistency to these equations. So that's a fantasy for how it would work in a complete theory of gravity. And then, so Shiraz asked, in the dual of n equals 4 Supering mills, can you compute the entropy using the replica wormholes? And I think the answer would be yes, you can get the right answer. But somehow it's not the whole story. Like, to understand the whole story, you have to understand what this other stuff is. Because that other stuff is important in interpreting it in terms of inner products. So it's like the microscopic data that should resolve the black hole information problem. Microscopic quantum data, inner products between states, discreteness of the spectrum, unitary evolution on those states. That data is not visible in the wormhole approximation. And the wormhole approximation is, however, good enough to compute the entropy. And if you take the wormhole description as the complete theory, then it describes an ensemble average. But if the wormhole approximation is just part of the complete theory, and there's a whole bunch of interesting UV stuff that we don't understand, then presumably it's not an ensemble average.
Okay, thanks.
Okay.
Thank you.
Yeah, thanks for the questions, you guys. Okay, so let's forget ensembles and confusions and return to things that make sense. Let's just try to make a small technical improvement. We computed the Renyi entropy, or the purity. Let's now compute the von Neumann entropy. So this can be computed using the replica trick. The von Neumann entropy is this quantity here, minus trace rho log rho. And we compute it by this limit of log trace rho to the n. So let's now ask gravity what it thinks of this expression on the right, trace of rho to the n. So the boundary conditions for trace of rho to the n are the following. We have n of these boundaries, and they're connected. The index contractions of the end of the world branes are connected in this cyclic fashion. It's this these boundary conditions here. And these can be filled in with gravity in various ways. I drew here two extreme ways you can fill it in. You can fill each one in with its own topological disk. That's a completely disconnected geometry. Or you can fill it in with a completely connected geometry, or there's all kinds of things in between. And what we want to do is, in principle, we want to do this whole sum over these things and analytically continue the whole expression to n goes to 1. But that can be done. It's a little complicated, and I'll draw you a plot in a second. But let's just, to start, let's just try to analytically continue these two extreme terms. They're easy to do. So let's first look at the completely disconnected term. If you look at the dotted line, there's exactly one loop. So there's one factor of k. And there's n disconnected disks. So we get k times e to the n s naught. At the other extreme over here, we have n dotted line loops. So we have k to the n, and we have one topological disk. So we have k to the n times e to the s naught. So if the first term dominates, so if k is reasonably small and the first term dominates, then we can just continue that term. And that's easy enough. That gives us the entropy log k. If the last term dominates, this completely connected geometry, this replica wormhole dominates, then the factors of k cancel. The k to the n here cancels the k to the n here. And we get an expression just involving s naught. And in fact, it's just s naught. So for small k, we get log k. And for very large k, we get s naught. So that's basically what we wanted to find. But, well, I have some discussion here of computing the von Neumann entropy more. But yeah, let me go through it because it's helpful for the next comment. So let's try to do a better job computing the von Neumann entropy. Here I just approximated it with the topological term in the action. If you actually want to compute the von Neumann entropy by taking by continuing this geometry, then you can do the following. So this is a famous manipulation which I think is really beautiful. It's like goes back to Gibbons and Hawking, but it was explained most clearly by Lukowitz and Maldacena. So it's like a really amazing computation. Well, it's a special case of a really amazing general computation. So the way it works is the following. We want to make sense of the continuation n goes to 1 of the action of this geometry. And I'm subtracting n times the disk for the normalization. So we want to take the limit n goes to 1 of the action of this thing minus n times the action of this thing. Now, the continuation in n of this object here doesn't really make sense because it has n boundaries and n has to be an integer for that to make sense. But what you can do is you can take the quotient. This has a Zn symmetry that rotates the thing by angle 2 pi over n. And if you take the quotient of this geometry by that rotation, then you get a geometry that looks like this. It has opening angle here, 2 pi over n. And the action of this pinwheel here is equal to n times the action of the quotient minus n times the contribution of the tip, of the action at this little conical singularity at the tip. And this is the subtle and beautiful part in this argument. You can see that there's no contribution from any conical singularity in the pinwheel here. So when we compute the action of the quotient, it does have a contribution from the tip, from a conical singularity, but it's fictional. It just arises due to the quotient. So we should subtract it. So now we can take the limit n goes to 1 just by changing the angle theta. As n approaches 1, theta approaches 2 pi, and we get geometries that look like this. Now, at order n minus 1, which is the order we need to work, the action of this geometry here completely cancels against the normalization factor, and we're left with just the contribution from the tip. So it's an amazing type of cancellation and simplification in the limit n goes to 1, where all we need to know about is the location very close to the tip here. And of course, that's the explanation of why the entropy of a black hole has such a simple formula. It's the area divided by 4g Newton. In principle, to compute the entropy of a black hole, you need to do some complicated thing where you analytically continue and compute the action, the on-shell action of the black hole. But the answer is very simple. It's just the area divided by 4g Newton. And the explanation for that is this argument here, that the whole computation reduces to the contribution of a conical singularity at this point. And that point is the location of the horizon. It's the area of the horizon. Okay, so if you analytically continue the pinwheel geometry, you find here we just conclude you get S naught, but that's in the approximation of just the topological term in the action. If you do the computation correctly, you find the entropy of a black hole. Okay, so putting these, to summarize our discussion up to this point, it looks like we're going to get this answer from these completely disconnected and completely connected geometries. Minimum of log k and S Bekenstein-Hawking. That's actually what we expected to get. That's like the analog of the page formula. And this formula is almost right, but to get the actual answer, you're supposed to sum over all geometries that have intermediate degrees of connectivity. And that problem can be solved, and it leads to this answer. It's a smoothed out transition between log k, that's this linear slope here, and S Bekenstein-Hawking, that's this sort of plateau value here. There's a particular smooth interpolating function that you get by summing over all the geometries that have partial connection. The fact that you can analytically continue in N, that sum, is kind of a magical fact. But it can be done. Okay, so that's the end of the discussion of the entropy in this simple model. Let me just make a comment.
Question?
Yeah. Yes.
Yeah. So if you actually follow the island prescription which is given, it seems that this phase transition always is a sharp transition. But it seems that what you have computed from gravity is giving me a smooth transition. So how do I modify the island prescription so that I'll get a smooth transition? Or what do you expect? Do you expect it to be a sharp transition?
Yeah, it should be. It's not just the island. It's any time when you have some holographic entropy computation where there are two contributions. We say that the holographic entropy formula says that you're supposed to take the minimum of the two, but it's not really right. The right thing to do is to do the full replica trick and then take the limit and goes to 1, and you're going to get some kind of smoothed out transition between the two. In most cases, the computation is too hard to actually try to do it. This model is simple enough that we can actually sum over everything with intermediate degrees of disconnection, and not only do that sum, but also analytically continue it to n goes to 1. So this model is simple enough that you can do the calculation correctly and you find a smooth transition. In other cases, for the island formula and just holographic entanglement computations more generally, there should be smooth transitions like this. They're just really hard to compute.
I see.
Actually, I think it's a fascinating question why there's some kind of fact about geometry that makes it possible to do a continuation in N. Like a continuation in N of the replica computations. It's not obvious from the description from the geometrical setup of the geometrical problem, but it should be true because we believe the answer can be continued in N. There's some fact that needs to be explained there that I don't know what it is. Okay.
Thank you.
Okay, so let me just comment briefly on, so far we've been discussing this really simple model. Whether the model was well motivated or not is up to you, I guess, but we can return now to try to think about the evaporating black hole. And what happens in the evaporating black hole is basically the same thing. The replica wormholes, so that we were able to analyze very easily in this model, they're harder to find explicitly. Like it's harder to find analytical solutions to gravity coupled to matter fields to give these replica wormholes. And nobody has constructed a solution yet, even for the simplest case, n equals 2. That would be for the computation of the purity. But because of this magical manipulation that we described here, it doesn't matter. In the limit n goes to 1, the replica wormhole disappears. It becomes an ordinary black hole geometry. The replica wormhole leaves this remnant. The remnant is the location of the Zn replica symmetry. Even in the geometry as n goes to 1, you can point to the location where the Zn symmetry fixed point would have been. And that location is the quantum extremal surface. It's like the Ryu-Takinagi surface. And the remnant of the equations of motion for the replica wormhole are the statement that that quantum extremal surface should, are the statement that that Zn replica symmetry fixed point should be at a locus of quantum extremality. So in the classical approximation, it's that it should be a extremal area surface. So this quantum extremality version of that was shown in a beautiful paper by Dong and Lukowitz. And this justifies the approach that reference 2 used a year ago. So it turns out that the justification of their method was a special case of the analysis already done by Dong and Lukowitz, as these authors pointed out. But I think it's important still to understand that at an intermediate step, we have these wormholes, and to understand the topology and the role of wormholes in actually getting this quantum extremal surface. It's kind of a miracle. Like, from the perspective of the Ryu-Takinagi computation, of the quantum Ryu-Takinagi computation, you have these different possible choices of extremal generalized entropy surfaces. And one of those corresponds to, in the replica computation, replica wormholes. And it's not so obvious from the limit n goes to 1. So, okay, so that is to say that the evaporating black hole works in a very similar way to the model that we just discussed. The difference is a technical difference, which is that the integer replica wormholes are harder to find analytically. You can find them in SYK. Okay.
Sorry, Douglas, may I ask a question?
Yeah.
So, I mean, these conclusions are general enough that one would be tempted to investigate them in some way in higher dimensions in a much more general setting as well, right? And you probably might have it in mind, but I want to ask you. I mean, I understand, and going back to the very beginning of this talk and the questions, there might be a subtlety. Let's say we want to try and do it in for the ADS5 coupled to asymptotic infinity, not just the near horizon of D3 branes, or some setting like this where we even just have 4-dimensional black holes in a,
you want something that's asymptotically flat?
Yeah, for example, or a more well-motivated example coming out of string theory, where we know for sure what the count of degrees of freedom are and so on. And, you know, it's not a, forgive me for using this word, it's not a cooked up model, all right? And I was just wondering what would be the issues if we were to just try and extend this calculation and say, well, we get extra, we say that it seems likely that there'll be extra replica wormholes, even though we can't find them at n equals 2, etc. The n equals 1 argument goes through because it's so simple. That seems something that should work more generally. I was just wondering, maybe one issue may be that here we were helped by the fact that the radiation region just didn't have any gravity in it. So there was a precise notion of what we meant by the entanglement of the radiation. But okay, that came up in the beginning, but maybe we can try to make that precise, and then we would just have a very general, precise argument.
I don't think there's any obstruction. I think it should work. I think yeah, I feel very strongly. I don't think there's really any subtlety. The only possible subtlety has to do with defining entanglement entropy in asymptotically flat spaces at infinity. And I think there's a technical question about whether you can insert twist operators at scri+. And I assume the answer is yes, but I don't know enough about asymptotically flat gravity to know that for sure.
Sorry, but can I say, I mean, there is within the setup you're considering, we could do that setup within n equal to 4 super Yang-Mills or anything else, where you just take the theory and you couple it to an external bath.
Yes.
And then you know from the boundary that, you do expect to get this kind of a page curve, because
yes.
you just have some ordinary quark gluon plasma. Everything is, you could just forget about gravity and just think about the system on the boundary. And so
yes.
you do expect to see this page curve. And then the question is, how do you reproduce this boundary dynamics from the bulk? But I mean,
yeah, but it is this computation, it's the quantum extremal surface does it. And the quantum extremal surface is the limit n goes to 1 of the replica wormholes.
I agree with that. The only thing is that it's not clear to me that, I mean, as we discussed in the beginning, that this is a good model for an evaporating black hole in 4-dimensional asymptotically flat spacetimes. Because in these models we're discussing, you've engineered a factorization of the Hilbert space by hand. And then I agree you expect to get this. But yeah, so
why shouldn't that be, I guess, like suppose we have some black hole in flat space, shouldn't it not matter too much, like whether it's in flat space or asymptotically ADS space? Like it's just radiating some Hawking radiation.
I don't know if you probably have more to say, but we could. Do you want to return? I mean, I have a few comments, but maybe we could come to this at the end of your talk if you have more to say. I can.
Okay. Yeah. Okay. Yeah. Fair enough. Okay.
Thanks. Sorry, I have what is probably an extremely stupid question, but please forgive me. This extremizing this quantum version of the Ryu-Takanagi formula.
Yes.
Takes a classical piece and a one-loop piece and extremizes it.
Yes.
And in interesting situations, the one-loop piece competes with the classical piece to give you something interesting like the island.
Yes.
In that situation, how do we know that the two-loop piece is not equally important? I mean,
well,
it's meant to be.
Yeah. I mean, one thing you can do is you can take a large number of bulk fields. So then, like, there's a large, so the classical approximation is good if the number of fields is large, because the entropy, although it's order 1, it's actually order the number of fields. So you're balancing a large thing against a large thing.
Okay, so good. So you could concoct situations where this is justified. But suppose we just had an ordinary black hole in flat space, and I want to know whether this extremizing the quantum classical plus one loop is quantitatively accurate. Would you expect that to be quantitatively accurate? For the question, for a situation that the one loop part, competes with the classical.
I expect okay, it's a good question, and I expect maybe there are some small fluctuations. If you only have order 1 bulk matter fields, it's possible there are some fluctuations in the location of the surface. I'm not sure. I haven't studied this. I haven't studied that.
Okay, thank you.
Let's see. Sorry. Well, while Douglas thinks, sorry, I thought that, let's say we take a pure theory of gravity in 4D, so we just have gravitons. I would have thought that the one loop contribution is small, and repeating the n equals 1 limit would just give us the black hole horizon. And that would agree with what you'd expect, that the final entropy of the radiation would track that.
Well, so an example where we can discuss this is, in the simplest examples, like for the eternal black hole, the quantum extremal surface is close to the bifurcation surface. So it's close to a classical extremum. So a small effect can move it slightly, and that's all you need in this case.
Sorry, can I ask, just to make this more precise? Maybe if you took a small black hole evaporating in ADS, not a big black hole and coupling it to an external path, but just a small black hole.
Okay.
You could describe everything within a single field theory.
Yeah.
Is there a good understanding of what is the computation one needs to do in that setup to obtain this curve?
No. I think that would be, from the boundary perspective, I think it would be a complicated thing you'd have to do.
Because if you took the full boundary, that the Ryu-Takanagi surface would just give you 0, right?
Yeah, it just easier. So you would need to identify some subsystem of the boundary theory that.
Precisely, but isn't that indicating that if you looked at, that's related to the problems we've discussed previously, right? The reason you're getting 0 is because the boundary always has all information about the interior. And the way you avoided the 0 in this setup was by creating an external bath. So, you hid some information from the boundary. You hid some information from the system you're looking at.
Well, wait. Okay.
So I would say that
that was a statement about the boundary theory, but not the bulk theory. I feel in the bulk theory, it's awkward in ADS because the radiation bounces back. But
now let's look at a small black hole. So it really evaporates. Like you can take it to be small enough. So the cosmological.
No, but it still evaporates, but the radiation could bounce. If we take it small enough, then the black hole evaporates before it even hits the boundary.
Very good, but even then, the entropy of the boundary is always 0 because the
entropy of the boundary is always 0, but the entropy of the bulk description near the boundary is not.
But is that so clear? If you believe the extrapolate dictionary, that entropy is also always 0, right? If you take the bulk region near the boundary, that also always has 0 entropy if you compute its exact entropy.
No, I don't think so.
The bulk operators near the boundary, if you believe that they are the boundary operators, then the entropy of the bulk region near the boundary is also always 0 in this setup.
Well, I don't think so. The bulk operators near the boundary, what type of bulk operators? Maybe it depends what type of bulk operators you're considering.
Precisely. So we could do two things. We could either consider all possible polynomials of bulk operators, like arbitrarily the algebra of bulk operators, or else we could decide that we are going to consider like only low point functions, like maybe only 2-point functions of bulk operators. But if we consider the low point functions, then it's not clear you get anything except for the Hawking answer. And if you consider the algebra, then you probably get the boundary answer, which is 0. So the question is, in the small black hole evaporating in a single CFT, what is the algebra that reproduces for you this?
Isn't there some parametric separation between the complexity of the operators that we need in order to compute the entropy of some small black hole and the complexity of the operators that we need in order for like the algebra near the boundary to actually be the entire algebra?
I don't think so, because I think you need to compute S-point functions in both cases.
Well, but S of what? Because we can have different sizes of black holes. Like S is not, that's what I'm thinking. Like the S that we need for the black hole is some kind of small s.
Yeah, correct. It's a small s. If it scales with n, but it's a small s, but it scales with n, some power of n.
Yeah.
And I think, yeah. So if you took s, you take the state and you have to have some notion of defining entropy with respect to a restricted set of correlators. But I would think if you measured S-point correlators, they would have information after the black hole is formed and after the black hole is evaporated. Can I say this way? The idea that you get a page curve somehow suggests that if you think of the boundary, you have this system that's thermalizing, is forming a quark-gluon plasma, and then it's evaporating into glue balls. But somehow there is some regime of complexity, some cutoff on correlators, which can extract information for you at later times, but cannot extract information for you at intermediate times.
Yeah.
But isn't that in contradiction with our intuition from statistical physics? So just to emphasize, this doesn't have anything to do with the setup you're describing. The setup you're describing, it's a clean problem. But
no, I know, but we're far from the.
Yeah, I agree. Yeah. And maybe also you should complete your what you wanted to say, as I said, and then we can come back to this.
Okay. Yeah.
Yeah.
Okay.
Sorry, Douglas, you have to go on, but I just want to make sure I understood your answer to a previous question. It'll just take a minute, forgive me. So if I understand what you said was, let's suppose we're trying to do this for some black hole in 4D. Let's say we've not put in artificially a large number of bulk scalar fields. We just have a few degrees of freedom like gravitons, etc. Now, it's true, of course, that the quantum extremal surface will move a little bit from the classical horizon because the one loop effect will give a small effect, I suppose. But wouldn't you expect that the final value, after you do the replica trick with the n going to one limit, would just agree with small corrections with the black hole entropy? And it remains to be done, but I'm just saying
yes,
the argument suggests that, right?
Yes, because the quantum extremal surface will be close to the horizon. So its area will be close to the area of the black hole, and the entropy will be close to the entropy of the black hole.
Right. Okay. Thank you. Please go ahead.
Yeah, I don't. Yeah. Okay. Okay. So let's see. So there's one other thing I want to discuss, and it's sort of a little bit difficult to get into, but let's see. So let's imagine that we're after the page time. So that in this model, what that means is that the entropy of the R system is equal to the entropy of the black hole. It's no longer log K. So K is very, very big. Then it follows from quantum information theory and computations of the entropy that the R system should describe the region behind the entangling surface. So I'm not going to explain why, but you can show that conditional on the entropy computations that we've done, it must be the case that the R system describes the region back here, that's shaded blue here, this island. So that's in the region where K is much bigger than e to the s. So what that means in practice is that by acting on the R system, this auxiliary system, we should be able to create a particle behind the horizon in this blue region. We should be able to put something there by acting in the R system, which naively has nothing at all to do with this black hole. It's entangled with it, but it's not causally related to it. So we know this from abstract quantum information theory reasoning. And what we would like to do is give a direct gravity argument.
So sorry, Douglas, I know we've been interrupting you a lot, but just to ask, because I don't know this abstract quantum information reasoning, what is the precise statement that you can actually prove that the entire region covered by an entanglement wedge, that all the information of that region must necessarily be contained, is it, on the boundary, and likewise for the radiation, is it? What is the precise statement when you say you can say this from abstract quantum information reasoning?
Yeah, so what you can show is that the way the argument goes is something like this. Let's put some object in the entangling, somewhere in the entanglement wedge. So let's put a spin here somewhere. And let's entangle that spin with some reference system, some other reference system. And now if we're able to compute all the entropies, the entropy between the system R and that reference system, just that reference system itself, system R itself, if we're able to compute all the entropies, then we can compute the mutual information between R and that reference system. And what we find is that the mutual information is large, which means that R contains a purification of the reference system. And the purification of the reference system is the spin that we put behind the horizon. So that means that the system R contains that spin. So the quantum information, abstract quantum information reasoning is actually pretty simple. It's just basically the statement that if you're holding something, okay, the way the game works is this. I'm holding two maximally entangled spins. I throw away one of them. I don't know where it went, but I keep the other one. You come and present me with some object, and you say, I can show that my object is maximally entangled with that your object is maximally entangled with my remaining spin, then I know that your object contains the spin that I threw away. It's a version of monogamy of entanglement.
I see. I see. I see. Okay. Thank you. Thank you.
Anyhow, the whole point of the discussion that I'm going to have now is that you don't need to know that kind of argument. You don't need to know quantum information theory to learn that this is true. All you need to know is gravity. So we're going to try in the last part of the talk to create a particle behind the horizon by acting on the radiation. And in order to have particles to create, we need to enrich the model slightly. So let's add a propagating field to our model in addition to the end of the world brains. So now we can consider states of the black hole where the end of the world brain is in state I, and we also have a state which we'll call A for the quantum fields. So the combined state is written psi I comma A, and it represents a state of our gravity theory where the end of the world brain is in state I, it's this part, and where the state of the bulk fields is in state A. So from the boundary perspective, we have some boundary condition here, which is a quantum state. Then we insert some operators A, and then we continue evolving. So that's the boundary description of this state. And the bulk description looks like this. We have an end of the world brain in state I, and then we have the bulk fields in some state. Okay, so that's some general class of states. To be simple, we're just going to be interested in two of them. So state 0 is an entangled state of our black hole system with a reference, as we've been discussing so far. In fact, it's exactly the state we've been discussing so far, with a vacuum for the bulk fields. And state 1 will be the same thing, except we have one particle behind the horizon, close to the end of the world brain. So we have these two states, 0 and 1. 0 has no particles, and 1 has one particle behind the horizon. And our goal, okay, what is it?
Question?
Yes? Mm-hmm.
Sorry. So is there a limit in which I can approximate the state psi I comma A with A? So is it like some sort of d Newton going to 0, or some limit in which I can approximate the ket psi I comma A as just ket A?
Well, they live in different Hilbert spaces. So this one lives in a completely well-defined Hilbert space. This is like the Hilbert space of the boundary theory, of the holographic theory. And the state A lives in the Hilbert space of the bulk effective field theory. So the sense in which they're approximately related is that this state of the Hilbert space, this exact state here, is approximately given by a bulk state where the bulk fields are in this state. But okay. I'm not sure if that answers your question or if you had something else in mind.
I was thinking of, can I think of ket A as a state of a field on the curved background, and psi A comma I comma A as a complete quantum gravity?
Yes, exactly.
Yes.
Yeah.
Okay.
Yeah.
Okay.
Thanks.
Thank you.
Yeah. Okay. So our goal here is to find an operator. So what it means to create a particle behind the horizon using the radiation is we need to find an operator that acts only on the radiation that turns this state into that state. So that's our goal, and we're going to do that in 2 slides. But I've tried to explain this before, and I've failed 100% of the time. So I'm trying a different thing, which is to insert this intermediate step. So just to get some kind of stupid geometrical fact out of the way that will help us with the next slide, because I think I'm not very good at explaining this. So here's a stupid geometrical fact that's going to help us in a second. Let's take this replica wormhole that we've been discussing. Forget about whether it has to do with replica wormholes or operators or black holes or whatever. It's just this geometry that we've written here. And let's imagine that we put a 4 pi conical excess in the middle here. So sorry, a 2 pi conical excess. So the total angle is 4 pi. And I just drew some black lines here for decoration. This geometry that I drew on the left is exactly the same thing as the geometry on the right. We have 2 of the standard disk-like geometries with little cuts. These two halves of these black line, these here are the left side of this vertical black line. And these two black lines here are the right side of the vertical black line. And if we glue these two things together along those black lines, then we'll create a 4 pi angle around this point, which is identified with that point, and we'll get this geometry on the left. So the notation on the left and the right are just equivalent notations for the same geometry, and it has this conical singularity in the center. Okay, so let's keep that in mind and get back to the thing we want to solve. Remember, the goal is to find an operator acting only in the radiation that turns this state 0 into the state 1. Okay, so here's a very naive try. So let's see, let me try to draw. So for a second here, just ignore this part. Then if we were able to write this operator, then it would clearly do the job. This turns state 0 into state 1. The problem with that operator is that it acts on the complete system, combined system, on B and R. It doesn't just act on R. So a very naive thing you can do is make an operator that acts only on R by just computing the partial trace over B of the operator that we know it works. And then multiply it by some constant that we'll have to figure out later. So this sounds like a ridiculously naive guess for an operator acting on the radiation, that on the R system that will do the job, but let's just see if it works. So if we write out the states 1 and 0 from the previous slide, these states here, and insert it in this expression, we find this form for the operator. So it's an operator acting on the R system, that's this factor, and then it has the matrix elements are just these inner products. So these things are numbers, and they're the numbers that you have to sprinkle in the matrix in the IJ basis to give the operator OR. Okay. So to see if this operator works at creating a particle behind the horizon, let's just compute a matrix element of this operator between two states, A and B, where A and B could both be either 0 or 1. Okay, if you use the formulas for states 0 and 1 that we wrote a second ago and plug in this formula for OR, then you'll find the expression written here. It's now a sum of products of these inner products. So remember, the inner products now have the states appearing in these state vectors have two subscripts. I, that's the state of the end of the world brane, and A, that's the state of the bulk matter fields. And we have various combinations of end of the world brane and matter field states in this expression. So structurally, it's quite similar to the computation of the purity. It's like a sum of squares of these inner products. And if K is very large, then the dominant contribution to this computation here will come from a connected geometry, just like it did for the purity. It will come from a replica wormhole. And okay, here's where the presentation gets a little dicey. This operator that I wrote here does not work in general. It's too simple. And I'll sketch for you what a better operator is in a second. But it's illustrative. Yeah.
The dominance of this replica wormhole saddle came from the fact that there was a factor of k squared, right?
Yes, yes.
And here, do we have these two loops, which will give you a factor?
Yeah, I didn't draw the end of the world brane loops, but they're there because they sum over I and j indices. So,
but they still end up being orthogonal because there is extra labels A and B and so on.
They still end up being, oh, the IJ states are still orthogonal, and the end of the world branes form loops that look like, let's see if I can draw them. There's a loop like this and a loop like that. So we have k squared for the two loops. I should have drawn them in blue, but I'm not very good at this. So yeah, so we get, yeah.
And
okay, so
just one more question. These operators, OR, you're looking for, they're very closely related to these mirror operators we constructed, right? I mean, we are trying to do something slightly different. We wanted guys who correctly entangled with the O's. But we
Yeah,
operators that inside. Yeah.
I think they are similar. It's mainly a difference of philosophy. So here we're going to show that using gravity that the operators work. In your case, you sort of defined the operators so that they would work.
Okay.
So, okay, so, sorry. Okay, so here's the part that's awkward to explain. The operator that I wrote here is not good enough. It doesn't work. And we'll fix it in a second. But it's useful to think about this case first, because it does work if we replace this wormhole geometry with a geometry where we allow a 4π singularity. So we shouldn't allow such a singularity, but let's just do it. And just for pedagogical purposes. And you can actually make cases where this works. It's like a fixed area state. Akers, Rath, Marolf, Harlow, Dong, fixed area state, but that's not too important. Let's just, by hand, put a conical singularity in this point in the middle of our wormhole. And then we'll see how this operator works. If that were somehow the case, that we had this conical singularity. And I'll fix it in a second. Okay, so we have this conical singularity here, which means that the wormhole geometry that dominates this expression can be written in the following way, with these two copies of our system glued together along these cuts. And my claim is that when we look at it this way, this does exactly what we want. This is exactly the bulk description of creating a particle behind the horizon. So let's try to explain that. The copy on the left, the replica on the left, corresponds to this factor. And that factor is the inner product in the Hilbert space of the physical black hole. Those things are leftovers from the physical states A and B. So this object here is the physical black hole that we're trying to create a particle behind the horizon of. We have a second copy of the black hole over here. What is that doing? That thing is computing these numbers that appear in the formula for the operator OR. So we're applying some operator to the Hawking radiation, and the numbers inside the matrix of that operator are computed using this black hole here on the right. So we have two replicas, the physical black hole, and this is some auxiliary copy of the black hole that we use to compute these numbers. So you should think of this black hole as living in the Hawking radiation. It's some quantum computer that's acting on the Hawking radiation. And the full geometry that we've described here, this replica wormhole, the particle that we're considering, the particle associated to state 1, is this yellow wiggly line. And it propagates from the place it's created over here on this boundary at 1, it propagates through the wormhole. So it propagates from the unphysical copy in the Hawking radiation into the physical copy of the black hole. And if we take this object here and glue it in on the left, then what we're gluing in is just precisely a creation operator. This is a creation operator for a particle because on the lower half of the cut, there's no particle. On the upper half of the cut, there's a particle. So that's the definition of a creation operator that we've inserted at this point in the physical black hole. So connecting this replica wormhole between the physical black hole and the quantum computer is precisely creating a particle behind the horizon. Okay, so that's how you see that the acting on the radiation can create a particle behind the horizon. The computation that you do in the radiation is described by a second copy of the black hole. That second copy connects by a wormhole to the physical copy, and the particle comes through the wormhole. That's how it gets behind the horizon.
So
okay.
Sorry, Douglas,
Yeah.
Can I ask a small question here?
Yeah.
So, I mean, is the moral of the story in a sense that operators acting on the radiation, which could actually, amount to simple operators inside the horizon, like creating a wave packet of a graviton or something, actually are very complicated operators when acting on the radiation, on the outside radiation.
Yes. Yes,
and
yes, that is true.
in effect are analogous to, even earlier in the ER equals EPR paper, Juan and Lenny had suggested thought experiments like take the late time radiation and turn it into a thermofield double of the surviving black hole. And then you could see why when you act on the late time radiation, you would have a pulse going in. And here it seems, of course, it's a Euclidean wormhole, but basically because the operator OR is complicated enough, in effect, you sort of create another copy of the black hole, at least in the wormhole situation. You have,
yes.
you have the Euclidean, you have the black hole, and then you have the quantum computer black hole, and they need to connect with each other. I mean, that seems to be the model of what you're saying, is it?
Yes, yes, you said it better than I did. Yes, yes, completely.
No.
The novel ingredient from the so I should have acknowledged that, these ideas have been around for a while in ER equals EPR paper, and before then in work that Suvrat and others have done. The thing we're adding to that here is showing that gravity shows you that it actually happens. You apply this operator, there's some non-trivial gravitational thing that happens. There's this wormhole. It's like a non-trivial solution to the gravity equations. And that explains why it's possible. So that we didn't put the wormhole in by hand. We found that the wormhole dominated the computation that we were doing.
Right. But sorry, just as a follow-up, and then I know it's very late for you, does the operator acting on the outside radiation, which amounts to creating a graviton wave packet inside, does it have to be as complicated as this? Does it have to involve a trace over BO like you had or something?
Yeah. Yeah. I think it probably does, yes, but I don't have a proof of that. I think it probably has to be very complicated. It's not even obvious from this expression how complicated the operator is, but I think it's an exceptionally complicated operator. Like the computational complexity of the operator is probably exponential. So it's a type of operator that we're not very familiar with.
Okay, thank you. Thank you very much.
But we don't need to know details of it in order to do this computation. Okay, so let me just try to say briefly what happens to this whole 4π business, which is that there's a better version of this naive formula that I wrote before. It's sort of similar. It involves a trace over B of the operator that obviously would have worked. So 0, 1, or whatever you want to put here. But it also involves some other factors, where these factors have a gravitational description. And I'm not going to explain them too much. Basically, you can analyze this quantity using a replica trick. And you take a replica trick that ends up eliminating the conical singularity. So in the same way that the von Neumann entropy is like a simple n goes to 1 limit of a replica calculation, this operator here is like a simple limit where the conical singularity goes away. So it works in general. And well, let me not say too much about this, but you can compute how well this operator works, and by doing in this model, by doing a summation over all geometries, disconnected and connected, partially connected, and you find that the operator transitions between not working at all, that means this coefficient C1 is small, and working very well, that means C1 is 1, at the page time. So the reconstruction of the interior using the operator in the radiation, the performance of that reconstruction can be computed in this model. It's this function here. It goes between 0 and 1 at the page time. So again, there's a smoothed out transition between being able to describe the interior and not being able to describe the interior. Okay, so that's it. Well, I guess I could summarize, but well, okay, no, I'm not going to do it. Let me just thank you all very much for your attention and for all the questions.
Thank you very much, Douglas. If everyone can perhaps unmute and clap. Okay, so we have had many questions during the talk, but if there are any more questions, Douglas, do you have some time?
Yeah, I do.
5 minutes or so, 5-10 minutes.
Yeah, I can. I'm
I
happy
have
to.
one. I
Yes,
have one
please.
question. So it's an old question about if you look at a boundary model of a black hole in terms of these plasma balls, which were described by Shiraz and collaborators, then there is this issue of the degrees of freedom inside the plasma ball, which are like gluons, open strings, and the degrees of freedom outside are glue balls in terms of local gauge invariant operators. Is this map that you talked about somehow related to asking the question about how do gluons actually, how do you write gluonic operators in terms of glue ball type operators? Is that I'm just, maybe a completely stupid observation, but. Because the glue balls are like the radiation, and there is stuff inside the plasma ball.
I think it's more complicated. I think it's more complicated than that. I think these operators are more complicated than that type of difficulty. I think they're, but I'm not sure.
Can I say, I think they're more complicated, Spencer, because they depend in detail on the form of the entanglement. The kind of question you're asking is some dynamical question. How do you write the glue ball operators in terms of gluons? This is a question that depends on the state, on what is the form of the entanglement. I think it's, slightly different question.
Subrat, you deserve a lot of credit for your early recognition of the need for these state dependence in these operators.
Sorry, Douglas, I have a vague question, but let me thank you for a really great talk and for taking our questions so patiently. Yeah. And I'm going to ask my question, but I wanted to ask you, would you be, although we've exhausted you, would you be willing to entertain a few questions later offline from some of us if we have them? Would that be possible?
Yeah, sure, absolutely. Mm-hmm.
Okay. My big question, Douglas, is the conclusion you came to based on your earlier paper with Steve and this one, that the Euclidean gravity, at least in this model, seems to be some kind of an average. Could it be that even in other instances, you suggested that in other cases, maybe this doesn't happen because there are more degrees of freedom. But could it be that Euclidean quantum gravity, which is a somewhat ambiguous theory, at least for some ways of doing the path integral, always gives some kind of an average answer, and it's different from the Lorentzian theory? And it always sort of gives a coarse-grained type of answer. I'm sorry, it's a speculative question, but I just want to ask you, and then we can chat later.
I'm not sure what the difference between Euclidean and Lorentzian quantum gravity is. I just don't know what.
You have to do the contour for the conformal factor in some ways, and you have to define the path integral. It's not an intrinsically well-defined thing without putting in some interpretations to it.
Okay, you're saying maybe Euclidean quantum gravity, the philosophy of Euclidean quantum gravity isn't actually well-defined in string theory, or?
At least
I feel like it should be, right? Like, and the continuation that you need to do to, well, I don't think there's any difference between them, and that the Lorentzian theory is probably defined by analytic continuation of the Euclidean one, or at least it's consistent with that. The duality with the CFT supports that view. So
maybe that's true, but you did have to do a continuation in the dilaton path integral, where you went from real to imaginary dilaton.
Yeah. Well, that was just to make the path integral well-defined, so.
Yeah, but in principle, you might have thought of other ways of doing that path integral. I'm just saying. I'm asking.
Well, I'm not sure if there's another way to define JT gravity non-perturbatively, but I'm not sure it's the most important question. Like, there are definitely other theories of quantum gravity that are much more interesting than JT gravity, and we shouldn't read too much into the answer that JT gravity is giving us. And the fact that JT gravity is an ensemble average could be a symptom of the fact that it's like a stupid two-dimensional model that has no degrees of freedom in it, and better theories of quantum gravity are not ensemble averages. On the other hand, it's also possible that, you know, both things are sort of generic. I'm really not sure what to think. But the fact that JT gravity is an ensemble shouldn't be interpreted as evidence that a specific version of n equals 4 super-Young-Mills doesn't have a specific gravity dual.
Sorry. Yeah.
Sorry. I was wondering, Douglas, if sorry, Sandeep, you have another question? Or?
No, I'm done. Thank you.
Yeah. I was wondering if I could go back to this question we discussed a little bit in the middle of the talk. Let's say we took a small black hole evaporating in ADS, so you could frame everything in terms of a single conformal field theory. And then, as we discussed, you know, you could either look at simple observations or complicated observations in the bulk near the boundary. I mean, do you have a sense of what you would need to do to get the page curve, or if there's something you could do to get the page curve? You see the question? The question is one of, you know, what is the complexity of observations you need to allow so that the entropy that you get obeys the page curve?
Yeah.
You know, one could frame it in another way. If you just think of the boundary, what's happening is you have some very small lump of the quark gluon plasma, and it's evaporating into some glue balls, and then you're allowed to measure some correlators of the glue balls, which are these correlators in the radiation.
Mm-hmm.
And the question is, you know, you restrict to k point correlators, where k is some number you need to pick, so that the entropy defined with respect to these k point correlators obeys the page curve.
Mm-hmm.
It's not clear to me that such a k exists, because, you know, if such a k exists, it would somehow suggest that k point correlators get more information after a certain time than they had previously. Whereas generally you would expect the system to become more and more thermal. So, you know, you'd expect a certain fixed complexity of correlation functions to get less information.
Wait, sorry. Can you say again why it needs to get more information?
Because the system, according to the page curve, should become more and more pure after a while. So you're measuring some k point glue ball correlators, and for some time it looked like things were becoming thermal in terms of these correlators. Yes. And after some time it looked like things became pure again.
But that must be true of evaporating coal or whatever, right?
Very good. But very good. But in this setup, it's slightly different, because you see, if you measured arbitrarily point correlators, the system already has all information. So there's no.
Isn't that like separate? Like, isn't that feels like it's a different kind of cutoff or something? The one that allows you to see the whole system. It's like a different kind of. It's a different K, isn't it?
Very good. You might have thought so. And in the case of evaporating coal, I think it is the case. You know, that, like, if you're looking at evaporation of 10 qubits, you know, you measure like 10 point correlators and you see the evaporation of qubits, but you switch off quantum gravity effects, because you'd never look at, you know, number of insertion scaling with n Planck. But I think in this setup, it's not clear to me that for an evaporating black hole, there is such a hierarchy of complexity. I mean, there might be, but naively, you would think that there is, you know, it's not.
Because I guess, let's see. Okay. So when you describe the operators, the subalgebra that it's operators out at the boundary, but at all times?
No, at a single time.
At a single time, but isn't the algebra that isn't an algebra, right?
No, you take all operators at the boundary and multiply them. That's an algebra.
But doesn't that actually generate? I mean, you can,
it'll generate everything.
so it's not really at a single time. It's operators everywhere.
Well,
They're all in the algebra. Local operators at the boundary at all times.
So I only want to start with operators at one time, but you're right that in the end, because of ADS-CFT, it'll generate everything. I mean, I don't want
I guess, okay. So I don't know. I'm like the last person to have a good view on to have a well-informed view on these types of subtle questions about operator algebras. There was some discussion about this at the KITP workshop this winter, and I don't remember it very well, but I imagine that you know this subject pretty well. So,
yeah, you know, my naive estimate, this is a very crude estimate, the one I'm about to give, is that you could look at correlators with complexity much smaller than S, or correlators with complexity of S. And in one case, I think you would get the Hawking curve, and in the other
which
case,
S? This is the S of the black hole?
S of the black hole, yes.
Okay.
And I think in one case, you'd get the Hawking curve if you just looked at low point correlators, like complexity much smaller than S.
Okay.
And I think in the other case, you'd probably have all information at all times.
Well, wait. I mean, so we could consider different sizes of black holes, right?
Yes.
And it seems like there's some, well, in the way that you're thinking about it, and I'm trying to imitate, like,
yes,
you need some type of complexity of correlators to reach into the bulk, right?
That's correct. But also depends on the complexity of the bulk state. So if you have, you know, so how complex the correlator you need also depends on how complex the bulk state is.
I see. And you say that dependence is like the same, that agrees with the dependence that you need to compute the entropy of the radiation. It's the same S.
It's a very crude estimate, but the crude estimate would be you need S in both cases.
Hmm.
I mean, it would be nice to have a much more precise estimate, but so in these, yeah.
So it sounds like you're saying that there must be some, like if we just study this in flat space, there must be some subtlety in defining the entropy of a piece of scribe plus.
Correct. I agree with that. Yeah, there is, and I think that, you know, if you just define the entropy of an algebra, I think you'd get zero. I mean, which is the algebra.
So does that mean you're not allowed to put twist operators, or that you're not, that doesn't give the entropy you want, or?
Yeah, I think before one looks at twist operators, it would be nice to understand what the definition of the entropy is.
I guess, okay, it's a matter of taste, but to me, like, the correlation functions of twist operators sound a lot easier than trying to understand, like, algebraic quantum field theory, but maybe you need it to understand the correlation functions.
Yeah, okay, maybe this is a difference of taste, but you know, the algebra on Scribe Plus is not too complicated. It's a free algebra, you know, because it's an asymptotic region. So,
okay.
And in fact, this algebra doesn't factorize precisely because you have these constraints. And it is, and you know, it's not clear to me what you would need to do to get something that obeys the page curve. If you just took the algebra, I think you would get zero. And it may be there is something that gives you the page curve, but it's not clear to me what that thing is. Maybe there's some subalgebra which gives you the page curve.
Huh.
Can I ask a small question to you, Subrat? Just maybe picking up on what Douglas was saying. Subrat?
Yeah, please go on. Yes, Sandeep.
May I? Sorry to intrude on this, but couldn't we define the location of the end of the Hawking radiation near infinity in some generally coordinate invariant way, even though we have gravity, you know, by saying shoot photons in some way and go some proper affine distance or grow some proper distance suitably? I mean, is that the subtlety that if you're trying to define the entropy outside a black hole where the other end, the end close to infinity has gravity, unlike in the model Douglas considered where there's no gravity in that part, you don't quite know what you mean by that region.
No,
otherwise, couldn't you locate the twist operator, as Douglas is saying, there, once you can locate that endpoint in a coordinate invariant way?
I don't think that's a subtlety in an algebraic term, Sandeep, because we could just work on Scribe Plus, literally on
No,
Scribe.
I understand it's not the subtlety in the algebraic way of thinking. I agree with you, Suvrat, but if you could make the endpoint precise in a generally covariant way, why couldn't you then do the replica trick path integral?
Okay,
and just
okay,
that's all I was.
That's a good. Yeah, I don't have a good. I mean, the question is, what is the replica trick path integral? What is it computing for you?
One possible problem, Sandeep, is that for some bulk region, you're not really allowed to compute the entropy in quantum gravity. Like that requires putting these twist operators, and I don't think you're allowed to put those in the bulk.
Yeah, but maybe near, I agree. It's not like I have a precise answer, but I was wondering near infinity where gravity becomes very weak,
yeah, it should be approximately allowed. Yeah.
Yeah, that's what I was trying to get at.
Let me ask another question, actually, related to a separate question. There's also the issue of the soft degrees of freedom. Would the replica trick computation see that? I mean, how does it see that? It's a slightly separate question from what we were discussing.
I'm not sure.
I mean, because we know there are these soft vacua, and there is some entanglement between the hard and the soft degrees of freedom. So presumably that should also matter somewhere. But in the replica trick way, it's just not clear to me where that comes about. So
I guess my excuse for not having thought about this is that you can work in 2 dimensions where there isn't really a bunch of this soft stuff, and that convinces me that it has nothing to do with the black hole information problem or the page curve or anything.
I mean, I tend to agree that it's not crucial, but I'm just mentioning it as something that is relevant in 4 dimensions. So if you were to define an honest entanglement entropy, it would have some trace of these soft degrees of freedom. You're right. You could go to systems where they don't exist at all, but in this setup, we know they exist. So the question is how you would like to capture them. In the algebraic perspective, it's clear they're there. I mean, you just have these different sectors, and you have to sum over them. You would get that contribution.
Sorry, could I button with an unrelated question and probably very stupid one? I'm trying to understand. I didn't completely understand this reconstruction part of your talk very well, so I'm sorry. What I'm asking may be silly, but I'm trying to understand what implications, this idea that part of the space-time can be reconstructed by a Hilbert space of an auxiliary system. What implications that might have for causality? Okay, so the naive question I have is this. I can throw something into the black hole from outside and it'll reach there in a short amount of time. However, by throwing something into the black hole, I shouldn't be able to affect a space, a state in the Hilbert space of something that's very far away, like the Hawking radiation, or completely decoupled like your R operator. Presumably throwing this particle in is not changing the state in the Hilbert space of this very far away region. So then how can it be that the particle there is a state in the Hilbert space of that far away region?
Okay, well, my initial reaction to this is that the operator that you have to use on the Hawking radiation will depend on, that one has to use on the Hawking radiation will depend on whether you came along and threw something in. So you coming along and throwing something in will change the state of the interior, and the operator that you have to use to decode will also change.
Okay, just to follow up, perhaps I should be clearer. I'm talking about you presented an operator on the auxiliary system that created a particle in the bulk.
Yes.
Now, I could presumably create that particle in the bulk by throwing that particle in from outside the horizon to inside the horizon.
Yes.
Okay, so Now, this throwing process, I would imagine, is a process that lies within the Hill. I can arrange it by doing some operation on the Hilbert space of the field theory.
Oh, no. It's behind the horizon. So it's not obvious that you can do it using the boundary theory, but sorry, by field theory, you mean the boundary theory?
Yes, boundary theory.
Yeah, so it's not obvious whether you can do it with the boundary theory or not, and it turns out in this case that that you can't. That region is described by the radiation and not by the boundary theory.
So, so it's not. I'm sorry. It's a very big question, but let me just express my discomfort. My discomfort is that two regions in space-time that are nearby can affect each other causally, easily. Whereas a disconnected quantum, you shouldn't be able to affect something very far away in a short time. So yeah. I was thinking that if in space-time, maybe it's inconsistent, but just in space-time, I throw something in, and it seems like you're telling me that by doing that, I've changed the state of the very far away Hawking radiation. And that just seems odd to me.
No, I'm not saying that.
I think you're asking different questions. I think Douglas is just saying that, the region behind the horizon is not described by the boundary degrees of freedom at late times. It's described by this auxiliary system. So
yes, but the region outside the horizon was described by the boundary degrees of freedom?
The region outside the horizon is described, yes.
Now I can start outside and throw something in.
Yeah, but it can change. So a good example, okay, whenever I get confused about anything, I think about the two-sided black hole. And that's a case where something like this is true. Mm-hmm. Things just to the right of the bifurcation surface are described by the right boundary. Things just to the left are described by the left boundary.
Good.
And they're close together in space-time, but they have different descriptions.
Good.
Sorry, can I say something? I don't know if it would help in what Shiraz is asking. May I say just a couple of things, Shiraz and Douglas?
Yes, please.
I was thinking that the answer to your question, Shiraz, may be the following. And Preskel and Hayden looked at something similar. Let's say we have a black hole which is past the page time. So it's very well entangled with the Hawking evaporation, with the Hawking radiation. Now we throw in a couple of qubits from outside. And we ask, what would it take to recreate this information just acting on the Hilbert space of the radiation? Which I think is the spirit of your question.
Right.
The answer is you have to wait a little bit of time, but not much. Just enough time so that if you threw in a few qubits come out. And then in principle, you should be able to recreate the qubits you threw in from the entire Hawking radiation, what existed before and the few additional qubits. But it's very well scrambled in all of this radiation, what came out already and what has now come out. And therefore, I thought what Douglas is saying is it won't be a simple operation on all of that Hawking radiation. It will be some very complicated operation, which amounts to the analog of creating the second side in the thermofield level. This is how I was putting it together. I might have added to the confusion.
Okay, thank you. I need to think this through. Yeah, thank you.
Oh, sorry.
I have a question about the last slide that you had.
Okay.
Before the summary slide.
Yeah.
So it's a small confusion. I thought that the operator which you have constructed, OR, should actually just act on the R system or the combined system.
Yeah, it acts on just the R system.
But the dot product is written between this effective field theory states.
So.
Yeah.
Okay. Where do you want to look?
Just above the page curve. Just above the page curve on the final slide. This is a operator element is between A and B states. I thought that should be either states from R or states which are combined of B and R system. Why is OR acting on the A and B states? It should only act on R.
So OR is an operator that acts non-trivially only on the R system, but we can compute its matrix element between two general states of the combined system.
But I thought you had said that A and B is only the effective field theory state, and which is also in the bulk. It's not in the R system at all.
Yeah, sorry. I use the same notation for two different things. So, sorry. The A and B here are either 0 or 1, and they refer to these states that were defined here.
Okay. So those states should be psi IA.
Well, no, because there are some over I of those things. We really need a third notation. So we should have called them capital A and capital B or something. They're the states of the combined system that have the effective field theory state A. Yeah.
All right. Yeah.
Hi, Douglas. So thank you for the very nice talk. I was wondering about something you had said in response to Sandeep's question about the Lorentzian and Euclidean gravity being not essentially different. However, I'm a little confused about that because at least if in JT gravity, the specific scenario that you're considering, I mean, there's a stark contrast between the Lorentzian and Euclidean picture, right? I mean, something that you yourself had emphasized in in one of the key papers with Maldacena and Yang, that in the Euclidean case, there's a whole family of zero modes, but in the Lorentzian case, it's the Hilbert space is essentially trivial because of the SL2 asymmetry. And I think this point was also emphasized by Daniel Harlow and Daniel Jaffries later. Could you please elaborate on that, or am I missing something?
Okay, let's see. Well, it's so in the Euclidean signature, you have these fluctuations in JT gravity, the boundary mode.
Right.
And that's like some degree of freedom as a function of time.
Yeah.
And the Hilbert space description of that thing is it's a low dimension. I mean, it's just like the quantum mechanics of just that particle or something. You don't see like the fluctuations in time in the Hilbert space description. But the one point I feel it's important is that this isn't a distinction between Euclidean and Lorentzian. This is a distinction between the path integral and the Hilbert space formalism. And they're compatible with each other. The difference, the subtlety is that in the path integral, it's sort of easy to see how you're supposed to include further topologies. And in the Hilbert space formalism, it's not very clear. And for that reason, I feel like the path integral is an easier starting point for thinking about quantum gravity than the Hilbert space. But there's no fundamental, it's not like there's two different theories, one in Euclidean signature and one in Lorentzian signature. There are two formalisms, the path integral and the Hilbert space, but they're compatible with each other as up to this question of topology. So I'm not sure. We could try to discuss it more in the specific case that you mentioned with the boundary modes on the disk. Would that be helpful, or what?
Yeah, yeah, something like that. Yeah, and that already helps a little. But yeah, it would be nice to discuss
perhaps this conversation
sometime later
carry out. You could perhaps chat or email Douglas about this at some later point. Well, thank you again, Douglas, for a wonderful and extremely clear talk. And let's thank Douglas again. Let's unmute our microphones and clap.
Yeah. Thanks, you guys. It was nice. It was nice. Thanks for the questions, and I hope you all stay safe and healthy.
Yeah.
Yes.
Likewise. Thanks a lot.
Bye.
Likewise,
Tremendous.
thanks a lot.
Tremendous.